Good morning. So, we will continue with our discussion on Bayes theory, the discussion that we started in our last class. So, we were discussing about Bayes decision theory. So, what we talked about yesterday is that suppose in a particular classification or pattern recognition application domain, we have a set of objects where we have for that particular object we have an observation say x. So, we have said that x is an observation and based on this observation we have to classify the object in one of the two classes. So, taking that particular example of a manufacturing industry, we have to classify that object either into the accepted category or in the rejected category. So, for doing this job, we have said that we have some a priori probability, that is p of omega 1 and p of omega 2, where omega 1 this category you have said that let us assume that this is the category of accepted objects and omega 2 is the category of rejected objects. And p of omega 1 is the a priori probability that the object will be accepted and p of omega 2 is the a priori probability that the object will be rejected. Okay. Now, in addition to make our decision, we have said that we have an observation x and for this observation x also we have class conditional probability density function, that is probability x given omega 1 and also probability x given omega 2. So, these two are the class conditional probability density function which we have to accept, which we have to estimate based on the measurements on x for objects which are known to belong to class omega 1 and the measurement of x from the objects which are known to belong to class omega 2. Okay. So, from these two we have to estimate this p of x given omega 1 and p of x given omega 2. But finally, our classification problem is that we have an observation x and based on this observation x, we have to put this object either in category omega 1 or in category omega 2. Or effectively what we have to find out is p of omega 1 given x and p of omega 2 given x. So, these are the two probability measures which we say are the posteriori probability. And based on these two probability measures, we have to decide whether the object has to be classified to class omega 1 or the object is to be classified to class omega 2. Okay. So, here p of omega 1 given x, we have said from Bayes rule that this is nothing but p of x given omega 1 into p of omega 1 upon p of x. Okay. Similarly, p of omega 2 given x is nothing but p of x given omega 2 into p of omega 2 upon p of x, while you find that this p of x appears in the denominator of both these expressions, where this p of x is nothing but p of x given omega I, take the summation for I is equal to 1 to 2. Okay. So, this is what we get from Bayes rule, and then our decision was like this, that if p of omega 1 given x is greater than p of omega 2 given x, then we decide in favor of class omega 1. So, in favor of omega 1. That means, we decide that the object having this observation x belong to class omega 1. If it is otherwise, that p of omega 2 given x is greater than p of omega 1 given x, then we decide that the object belongs to class omega 2. However, you find that we have one condition, that if p of omega 1 given x becomes equal to p of omega 2 given x. Okay. So, this is the case when we cannot take any decision, because the object lies on the decision boundary between the class omega 1 and omega 2. So, it may be both in class omega 1 as well as class omega 2. Okay. So, this is the case where the decision cannot be taken. Okay. So, this was the basic Bayes decision theory, where we have taken that we have two classes omega 1 and omega 2, and our decision was one of the two decisions, either the object has to be put in class omega 1 or the object has to be put into class omega 2. Okay. Now, there can be a generalization of this Bayes theory. So, the generalized Bayes theory can be put something like this. So, instead of classes, let us call it the states of nature. Okay. So, earlier in the example that we have taken, there are only two states of nature. Now, we can generalize it having multiple states of nature. Okay. So, the first generalization is like this, that use more than two states of nature. Okay. And then the states of nature in our case, in this classification problem, is nothing but the classes. So, that will be our understanding. When we talk about, when we say that states of nature, in our case it is nothing but the classes. Okay. In the earlier case, we have taken a single observation x. Okay. So, based on this observation x, we have tried to decide whether we have to put the object into class omega 1 or we have to put the object into class omega 2. Now, in the generalization, we allow more than one observations. Okay. That means, instead of having a single feature, we allow feature vector. Okay. So, use more than one features. So, that means we are going for feature vector. Okay. The other generalization is, in the earlier case we had only two actions, that is either decide about class omega 1 or decide about class omega 2. Okay. So, now we can allow a number of actions instead of just deciding whether this belongs to class omega 1 or this belongs to class omega 2. So, just this case I have shown that if p omega 1 given x equal to p omega 2 given x, I cannot take any decision. Okay. So, this particular fact that I cannot take any decision, I can also define this as action. Okay. That I cannot decide to which class the object belongs, that also I can call as an action. This no decision is also action. So, I can allow other actions other than merely deciding states of nature. So, when as I said that states of nature in our case is classes. So, merely deciding whether this object belongs to class omega 1 or the object belongs to class omega 2, apart from that I can take other actions as well. Okay. And the third one, the fourth generalization is this, that in our case our decision was based on posteriori probability, that if p of omega 1 given x is greater than p of omega 2 given x, then we decide in favor of omega 1. If it is the other way around, that is p of omega 2 given x is greater than p of omega 1 given x, then we decide in favor of class omega 2. Okay. So, in this case we can have a more generalized criteria based on which we can decide about the states of nature, which is called a loss function. So, we introduce a loss function which is more general than probability. Or let us say probability of error, because as we said that if we decide in favor of omega 2, then the probability of error is p of omega 1 given x. Okay. And the purpose was to reduce the probability of error in simple Bayes decision theory. Okay. So, as I said that we will have more than one states of nature. So, let us assume that there are c number of states of nature or c number of classes, to be more specific in our application, and those classes let us call a set of classes omega 1, omega 2 up to say omega c. Okay. So, there are c states of nature. Okay. Now, about the actions, as we also said that we also allow actions other than merely deciding about the states of nature. Okay. So, suppose there are a number of actions. Okay. So, I have this set of actions which I represent as alpha 1, alpha 2 up to alpha a. Okay. So, this is the set of actions that I have, apart from simply deciding that whether the object belongs to class omega 1 or it belongs to class omega 2 and so on. Okay. So, I have this a number of actions, and I said that we introduce a loss function which is more general than probability of error. So, this loss function I represent as lambda alpha I given omega j. So, this means that if the actual states of nature is omega j, whereas we take an action alpha I, okay, then the loss incurred while taking this action alpha I, when the actual state of nature is omega j, is lambda alpha I omega j. Okay. So, this is loss incurred for taking action alpha I when true state of nature is omega j. Okay. And the fourth generalization we said that instead of considering a single feature, we will consider a feature vector. So, here let us assume that we have a feature vector, that instead of a single feature we have a feature vector, that means multiple number of features or multiple observations of various parameters, okay, which is a vector x, feature vector x, and this feature vector x is d dimensional. Okay. So, these are the things that we have c number of states of nature given by omega 1 to omega c. We have a number of actions from alpha 1 to alpha a. We have a general loss function which is given by lambda alpha I given omega j, that means the loss incurred for taking an action alpha I when the true state of nature is omega j, and we consider a feature vector x which is a d dimensional feature vector. Okay. Now, let us see that how this decision rule in this generalized Bayes theory has to be taken. Okay. So, suppose we have an object, and for that object we have made an observation vector or the feature vector given by x. So, x is the feature vector which is of dimension d, and for this feature vector we take an action alpha I. Okay. So, as we said earlier that the loss incurred for taking an action alpha I while the true state of nature is omega j is given by lambda alpha I omega j, right. So, here for this feature vector x, from this observation x we have taken an action alpha I, but we do not know what is the true state of nature. It may be omega 1, it may be omega 2, it may be omega 3 and so on. The true state of nature may be anything. So, for each of this I will incur a loss function, right. So, if the true state of nature is omega j, I incur a loss which is given by lambda alpha I given omega j, okay. And if the probability that the true state of nature is omega j given that feature vector x, okay, then the average loss or the average risk can be computed like this. This average risk or expected loss can be r alpha I given x is equal to lambda alpha I given omega j into p omega j given x, okay. X is my observation vector, take the summation over j is equal to 1 to c. Is that okay? Because I do not know what is the true state of nature. So, if the true state of nature is omega j, then my loss function is lambda alpha I given omega j. Then I have to multiply this with the probability of true state of nature being omega j given my observation vector x. So, this is lambda omega alpha I given omega j into p omega j given x, take the summation over all the states of nature, that is j is equal to 1 to c, that gives you the expected loss, okay. So, which we are calling as r of alpha I given x, okay. So, this expected loss is also called a risk function. Okay. Or we can also call it conditional risk, because it depends upon x. Okay. Or it is also the expected loss. Okay. So, any decision or any action alpha I that I have to take, I have to take that particular alpha I, that particular action for which this risk is minimum or the expected loss is minimum. Unlike in the previous case, where we used only 2 classes, our decision was taken in favor of that class which gives us minimum error. That is, if I decide in favor of omega 1, I make sure that the error is minimum, which is nothing but p of omega 2 given x. Similarly, if I decide in favor of omega 2, my error is p of omega 1 given x, which is minimum in that case. Okay. In the generalized case, I have to take that action alpha I for which this risk alpha or alpha I given x is minimum. Okay. So, accordingly, this is also called minimum risk classifier. Okay. So, in this generalized case, the kind of classifier that I will have is a minimum risk classifier. Okay. Now, later on we will see various derivatives of this minimum risk classifier. It is this minimum risk classifier which under different conditions leads to different kinds of classifiers which are actually in use. Okay. So, let us see a 2 category case. Suppose I have 2 classes omega 1 and omega 2 or 2 states of nature omega 1 and omega 2. So, in this case, and if I assume that the action means saying whether the object belongs to class omega 1. Okay. So, alpha 1 means that decision that the object belongs to class omega 1, alpha 2 means decision that the object belongs to class omega 2. Okay. So, I have 2 states of nature, one is omega 1, other one is omega 2. Okay. So, as I have this omega 1 and omega 2 and also I have action alpha 1 and alpha 2, these are the actions. So, action alpha 1 means decision that the object belongs to class omega 1, action alpha 2 means deciding that the object belongs to class omega 2. Okay. So, over here now if I write lambda alpha I given omega j, okay, as say lambda I j, just for simplicity of expression. Okay. So, lambda I j means lambda alpha I given omega j, that is the loss incurred for taking an action alpha I when the true state of nature is omega j. Okay. So, for this 2 class problem, I can have risk function r of alpha I given x, as we said, is nothing but lambda alpha I given omega j into probability omega j given x. We took the summation for j is equal to 1 to c for all possible 2 states of nature. Okay. So, in our 2 class problem, these expressions simply becomes that if I take action alpha 1, so I will have r of alpha 1 given x, okay, this will be lambda 1 1, that means lambda alpha 1 given omega 1, is that okay, into p of omega 1 given x plus lambda 1 2, that means lambda alpha 1 given omega 2, okay, into p of omega 2 given x. If I expand the loss function, the expected loss for taking an action alpha I on an observation vector x, then this is the expansion of the loss function, the expected loss function or the risk function. Similarly, I have the other option of taking action alpha 2. Okay. I can take one of these 2 actions. So, the risk involved for taking action alpha 2 on observation vector x is nothing but lambda 2 1 okay, into p of omega 1 given x plus lambda 2 2 into p of omega 2 given x. Okay. Now, as I said that I have to take that action for which the risk is minimum. Okay. So, if I find after computation of r of alpha 1 given x and r of alpha 2 given x that r of alpha 1 given x is less than r of alpha 2 given x, then I have to take action alpha 1. If it is otherwise, that of r of alpha 2 given x is less than r of alpha 1 given x, then I have to take action alpha 2. Okay. So, under that condition, for deciding in favor of class omega 1 or for taking an action alpha 1, where r of alpha 1 given x will be less than r of alpha 2 given x, you can find that this leads to a condition that lambda 2 1 minus lambda 1 1 into p of omega 1 given x. Okay. This has to be greater than lambda 1 2 minus lambda 2 2 into p of omega 2 given x. Okay. So, this is the condition if I have to take decision in favor of class omega 1 or if I have to take action alpha 1. Okay. Now, over here you find that this lambda 1 1 means taking an action alpha 1 when the true state of nature is omega 1. And as we are saying that in our case taking an action alpha 1 means deciding that the object belongs to class omega 1. So, we are taking the correct decision. Similarly, lambda 2 2, okay, this is the loss incurred for taking an action alpha 2 when the true state of nature is omega 2. So, this is also a case when we are taking a correct decision. So, this is loss involved for taking correct decision, right. Whereas, this lambda 2 1 and lambda 1 2, these are the loss for taking wrong decision, because we are taking action alpha 1 where the true state of nature is actually omega 2, or we are taking an action alpha 2 when the true state of nature is actually omega 1. So, naturally this alpha 2 1 will be much larger than alpha 1 1, because this is loss for taking correct action. Ideally, this should be equal to 0, because the action is correct. Similarly, lambda 1 2 is much greater than lambda 2 2, because this is also the loss incurred for taking wrong decision, whereas lambda 2 2 is the loss incurred for taking a correct decision. So, you find that both of these, that lambda 2 1 minus lambda 1 1 and lambda 1 2 minus lambda 2 2, both of them will be positive or greater than 0. Okay. Now, I can compare this with the two case or Bayes decision that we have taken earlier, or minimum error classification that I have taken done earlier. Okay. So, over there our condition was p of omega 1 given x, if it is greater than p of omega 2 given x, then we have decided in favor of class omega 1. Okay. Now, in case of this generalized one, by incorporating the risk function, that is in minimum risk classifier, what we have to do is this decision rule that we had taken in simple Bayes decision, okay, that actually has to be weighted by the loss difference, okay, because this lambda 2 1 minus lambda 1 1 is nothing but a loss difference for taking a wrong decision and for taking the correct decision. Similarly, lambda 1 2 minus lambda 2 2, this is also a loss difference between taking a wrong decision and taking a correct decision. Okay. So, the difference between our generalized case and the specific case is that here we had the simple expression p of omega 1 given x minus greater than p omega 2 given x leads you to the decision of omega 1, or in the present term action alpha 1. If it is the reverse, then I have to take action alpha 2. Okay. Whereas, in minimum risk classifier, this simply becomes lambda 2 1 minus lambda 1 1, which is weighting this a posteriori probability p of omega 1 given x. Okay. That is greater than lambda 1 2 minus lambda 2 2 into p of omega 2 given x. This actually initiates action alpha 1 or deciding in favor of omega 1. Okay. So, this is what we are getting following the minimum risk classification. Now, as I said that there are derivatives of this minimum risk classification. Under different situations, I can have different types of classifiers which are actually derived out of this minimum risk classifier. Okay. So, let us see one such classifier, which is minimum error rate classifier. You have any questions so far? Any question?
Sir, how will we measure lambda 1 and
Those are predefined. The loss functions are predefined. Depending upon the kind of application that you have to define what is the amount of loss that you will impose for different wrong decisions or for a correct decision. Okay.
So, what means loss incurred for correct decision?
Ideally, it is 0. If I take a correct decision, then the loss is actually 0. So, ideally it should be 0. However, for more generalization, I can still put a loss function which may be very low. Okay. Because as we said in our previous class that even if I take a decision omega 1, but the probabilistic point of view, there is also a finite probability that the object may actually belong to class omega 2, though that probability value is very small. Okay. So, ideally the loss involved for taking a correct decision is 0, but to take care of such cases I can impose a loss even in a correct decision, but that loss value may be very low. Is that okay? Because there is always a finite probability that my decision, even though I am confident that I am taking a correct decision, but there is a finite probability, however small it is, that my decision can even be wrong. Okay. So, that is taken care of by that lambda I or lambda j j. That is, even there is a situation that I may incur a loss, even if I am confident that I am taking a correct decision from other circumstances. Okay. So, what is this minimum error rate classification? Okay. So, we said that if I take an action alpha I, that means I am taking a decision that the true state of nature is omega I. That is alpha 1 means true state of nature is omega 1, alpha 2 means true state of nature is omega 2, and so on. Okay. And if I define the loss function like this, say lambda alpha I given omega j. Okay. So, taking an action alpha I means deciding that state of nature is omega I. Okay. So, as I said that if my decision is correct, that means if I take action alpha I and the true state of nature is also omega I, then ideally I should incur a 0 loss. Okay. So, if I define this loss function like that, so I define this lambda alpha I given omega j is equal to 0 whenever I is equal to j. Okay. That means I am taking the correct decision. And the loss function I make equal to 1 whenever I is not equal to j. Okay. So, this is how I define my loss function. Okay. And this is true for all I and j equal to 1 to c for all different values of I and j. So, whenever I and j are same, that means I am correct decision, I am taking a correct decision, the loss involved is 0. Whenever I take a wrong decision, the loss involved is 1. Okay. So, this is how I define my loss function. So, by this definition of loss function, let us see that what will be the expected loss or the risk, that is R of alpha I, okay, given x. That will be nothing but, as we have already said, alpha I given omega j into p of omega j given x, where j varies from 1 to c. So, this is the loss involved or the risk involved for taking an action alpha I, right. So, over here you find that what is the nature of this lambda alpha I given omega j. This is either equal to 0 or equal to 1, right. So, it is equal to 0 whenever I is equal to j, and it is equal to 1 whenever I is not equal to j. So, this term, this summation gets simplified to summation of p of omega j given x, okay, wherever I had I is equal to j. Is it not? Because only when I is equal to j, this lambda alpha I given omega j, that was 1. Sorry, wherever I was not equal to j, this summation lambda alpha I given omega j equal to 1, and wherever I was equal to j, this was equal to 0. So, this summation will be wherever I is not equal to j, okay, not I equal to j, right. Now, for this alpha I have only one value of I, only one value of j which is equal to I. Total summation of all these probability values p of omega I given x or p of omega j given x for all values of j is equal to 1. Out of that, this is the summation where I is not equal to j, right. So, and this is nothing but 1 minus p of omega I given x, right. So, if I want to maximize or minimize this risk function, that means this term has to be minimized, and if I want to minimize this, then this p of omega I given x has to be maximized. Okay. So, you find that I come back to the same decision, similar decision in the generalized case, that p of omega I given x, for whichever I this is maximum, I have to take that decision, okay, and that ensures minimum risk, that ensures minimum error rate. Okay. So, this minimum risk classifier in this particular case boils down to minimum error rate classifier. Okay. So, that is why I said that starting from there I can have various derivatives various types of classifiers. But finally, all of them will turn out to be equivalent, but under different situations I can use them differently depending upon our convenience, how we can model our problem in a particular domain. Okay. Now, let us come to another concept which is called a discriminant function. So, effectively what are the classifiers that we have? See, it is something like this, that yes.
For that I equal to j, anyhow that particular term will be 0 also.
Which one?
In this particular previous summation.
Yeah, I equal to j.
For I equal to j, that particular term will be multiplied. This probability will be multiplied.
Probability is not 0. Lambda alpha I given omega I is 0. That is why the term is absent from here. Here we are taking this probability p omega I given x. P omega I given x is not 0. But in this expression, this p of omega I given x was to be multiplied by lambda I. This lambda I is 0. That is why in this expression, this p of omega I given x, the term corresponding to this is absent. It is only because of this. P of omega I given x is not 0. Okay. So, when I have this C class classifier, I can put it something like this. So, I have a classifier. Let us assume that it is a black box. Okay. So, this is my classifier block. Okay. Input, I have an observation vector or feature vector x of dimension d. Okay. Then the classifier has to give me a decision that what is the class belongingness of this object having this feature vector x. Okay. Now, inside this black box, all these different types of calculations are to be done, are to be made. Okay. If I go for minimum risk classifier, then for every different action, this classifier has to find out that what is the corresponding risk, and it has to give me that action for which the risk is minimum. Okay. If I go for Bayes rule, for every different class, it has to find out what is the a posteriori probability, then whichever class gives me the maximum a posteriori probability, the classifier will decide in favor of that class. In case of minimum error rate classifier, for every class, the classifier has to decide that what is the error for taking a particular action, okay, and it will decide in favor of that action which gives you minimum error, right. And you find that I have to compute the number of functions which is equal to number of classes, or which is equal to number of actions that I have in my classifier. So many functions are to be computed. So, for every action alpha I, okay, where is, yeah, for every action alpha I in my classifier, I have to compute this R of alpha I given x. For every class omega I have to compute this P of omega I given x, like that. So, it is the number of classes or the number of actions that I define with my classifier, I have to compute so many functions. Then whichever function gives me either maximum or minimum, I take that particular action or decide in favor of that particular class. So, I can say that in this classifier box, I have different modules or functional units which computes a function g of x. So, this computes g of x, g 1 of x, this computes g 2 of x, this computes g 3 of x, this computes g c of x, okay, on the same feature vector x. Then you it takes a decision either following the maximum criteria or following the minimum criteria, that to which of these C number of classes this feature vector x should belong. Okay. Now, if I put a generalization that I will always compute the maximum of these functional values. Okay. So, out of these C number of functional values, whichever functional value is maximum, I will put x into the corresponding class. Okay. So, over there these functions are what are called as discriminant functions. Okay. So, this g x is called discriminant function. Okay. So, your function is same, I will call it g 1 x when it is computed for class 1 omega 1 or when it is computed for class omega 2. G 2 x, it is the same function g x when it is computed for class omega 2 or for alpha or for action alpha 2 and so on. Okay. So, this function g x is called discriminant function, and whichever class gives you maximum value of the discriminant function, I put this object into that corresponding class. Okay. So, now let us see that what will be the nature of this discriminant class. So, when I have C number of classes omega 1 to omega c, so there are C number of classes. Okay. So, I will have C number of the functional values of the discriminant function. So, g I x for I varying from 1 to c, right. So, if I feel the decision rule in general that g I x is greater than g j x, okay, for all j not equal to I, okay, then I decide that this x belongs to class omega I. Okay. So, this means that whichever g I x, whichever class I gives the value of this discriminant function g I x maximum, because this g I x greater than g j x for all j not equal to I means that this one is maximum. So, for whichever class this discriminant function gives me maximum value, I put x into that corresponding class. Okay. So, what will be the nature of this discriminant function under different conditions? If I go for minimum risk classifier, okay, my risk is given by R of alpha I given x for taking an action alpha I, okay, and the risk has to be minimum to take an action alpha I. But in terms of discriminant function g I x, the value of the discriminant function has to be maximum. So, naturally, if I want to relate this risk function with the discriminant function, I have to make g I x which is negative of R of alpha I given x, because whenever this is maximum, this is minimum because it is negative, and whenever this R of alpha I given x is minimum, by negating this g I x becomes maximum. Okay. Similarly, for minimum error rate, okay. For minimum error rate classification, my condition was that this 1 minus p of omega I given x, that has to be minimum. That means, p of omega I x given has to be maximum. So, I can simply equate g I x to p of omega I given x. Okay. So, for minimum error rate classification, GIX is simply P of omega I given x. Okay. So, I can have the discriminant functions like this, and for multiple number of classes, for whichever class the value of the discriminant function is maximum, I put x into that particular class. Okay. Now, find that I can define GIX like this, but the choice of the discriminant function GIX is not unique. The reason is, if I take a function f, say I have this GIX, and I take a function which is function of GIX. Okay. Now, if this function f, which is function of GIX, this is monotonically increasing. Okay. Then also this f of GIX will serve the same purpose as GIX, because it is monotonically increasing. Okay. So, for whichever I GIX is maximum, for the same I f GIX will also be maximum, because the function f is monotonically increasing. So, if I can identify GIX, then for any monotonically increasing function f of GIX, that will also serve the same purpose of discriminant function. So, this discriminant function that I said GIX, it is not really unique. I can have various types of discriminant function. So, only care I have to take is this function f that I have to choose, that must be a monotonically increasing function. And that gives us an advantage in the sense that if somehow I can identify GIX, but GIX in its original form, if it is not mathematically tractable, I can take another functional of this GIX which can be mathematically tractable, and that can be used as discriminating function. Okay. So, coming to a very simple example. So, coming to this minimum error rate classification, we have said that this GIX is nothing but P of omega I given x. Okay. If I expand this, it simply becomes P of x given omega I into a priori probability P of omega I upon summation of P x given omega j into P omega j for j varying from 1 to c. Okay. Now, find that this term P x given omega j into P omega j, because this is nothing but our P of x, this is nothing but P of x. Okay. And because this term is appearing in the denominator of all the discriminant functions, for every value of I, this will be there in the denominator. So, I can simply remove this when I design my discriminant function. So, I can say that my discriminant function will simply be GIX is equal to P of x given omega I into P of omega I. This will be my GIX. Okay. Now, find that when I define GIX like this, there is a product term, and whenever I have a product, it is more difficult to implement as well as analyze rather than if I have a summation, right. So, as I have in my original formulation GIX like this, we know that logarithmic function is also monotonically increasing function, right. So, instead of using this, I can use log of this, and that can be my discriminant function. Okay. So, instead of using GIX as this, I can use GIX as okay. This can also be my discriminant function, and here I have avoided this product by summation. Okay. So, it becomes mathematically more convenient, right. Now, using this, if I go for a 2 category case, that is I have say classes omega 1 and omega 2. That means I have classes omega 1 and class omega 2. So, when I have these 2 classes, that means I will have 2 discriminant functions. One is g 1 x, other one is g 2 x. And my decision rule is, if g 1 x is greater than g 2 x, I decide in favor of omega 1. If g 1 x is less than g 2 x, I decide in favor of omega 2. Okay. So, what is the decision boundary between the classes omega 1 and omega 2? Decision boundary is simply where g 1 x is equal to g 2 x. Okay. So, g 1 x minus g 2 x is equal to 0, that gives me the decision boundary. So, if g 1 x minus g 2 x is greater than 0, I put it in class omega 1, if it is less than 0, I put it in class omega 2. Okay. So, I can say that instead of taking these 2 discriminant functions, particularly in a 2 category case, I can have a single discriminant function which is given by g x is equal to this g 1 x minus g 2 x, and if this is equal to 0, that gives me the decision boundary, right. And from here, by applying this same concept of logarithm, you will find that this discriminating function can now be written as, and if I use g 1 x to be p of omega 1 given x and g 2 x to be p of omega 2 given x, then g x becomes p of omega 1 given x minus p of omega 2 given x. Okay. And using the concept of logarithm, and by expanding this in terms of a priori probability and class conditional probability, this will simply be written as ln p of x given omega 1 upon p of x given omega 2 plus ln p of omega 1 upon p of omega 2. Okay. So, here I have this a priori probabilities as well as class conditional probabilities. So, when the a priori probabilities are same, you find that this term becomes equal to 0. So, only decision is based on your class conditional probabilities. Okay. So, I will stop here today. We will continue with this discussion in the next class. Thank you.